Welcome back. AP Calc Review, Applications of Integrals. We're going to be covering area, how to find area with integrals, finding net change. We're going to talk about accumulation functions. We're going to talk about average value. This year's exam will not have finding area between two curves. It will not have finding volume, so that is not going to be covered in this review. Using integrals to find area. One of the big things is understanding that this question is not the same thing. Finding the integral from 0 to 5 of f of x dx, and finding the total area between f of x and the x-axis from 0 to 5. Finding this integral just means, calculate the integral from 0 to 5. Yes, integrals find area, but the value of this portion of the integral is going to be a positive, and anything below the x-axis, that's negative, right? So if I want total area, whenever it says total area, like watch out for that phrase, whenever it says total area, it's saying treat this like a positive area. So to do that, I'm going to be making use of Desmos. It occurred to me, hold on one moment, that with the AP exam the way it is, you can use whatever calculator you want. I like Desmos a lot more than I like my graphing calculator, my handheld one. So I use Desmos. If I wanted to calculate the integral of this function from 0 to 5, I just wrote f of x equals that thing. So the next line, I can just calculate under functions, miscellaneous integrals right here, the integral from 0 to 5 of f of x dx. It won't do it unless you have that dx, 10.41. However, if it asks for the total area from 0 to 5, I need to treat this area part and that part separately. That spot right there does happen right at 3. Desmos is nice. When I highlight it, it says, oh, that happens right at 3, 0. So I'm going to calculate, there's lots of ways you can do this. The way I tend to do it is I tend to calculate these integrals separately. I'll say I want to find the integral from 0 to 3 of f of x dx. And then I know that's negative, so I would probably just say minus the integral from 3 to 5, right? Because minus and negative is positive. Hey, look at that, 21.08. Definitely bigger than that because it's now counting that as a positive value. Other people like doing it by just saying absolute value of f of x, right? Because absolute value takes something and turns it positive. Right? If I did that, I'd take these negative numbers, flip them up right here, and it'd be the same positive area there and there. Same answer, however you like to do it. All right, going back. Using integrals to find net change. That's not a bad one. Here's an example. It says the above graph shows the rate of change in the weight of an animal in ounces per week over a 30-week period of time. Which of the following is closest to the total change in weight of the animal in ounces during the 30 weeks? Well, this axis is being measured in weeks. That axis is being measured in ounces per weeks. If I take ounces per weeks times weeks, those weeks cancel out, and I just end up with a value of ounces. So I really want to find the area under that curve, right? That's how net change works. The integral of a rate gives me a net change in my amount. So I just need to calculate the area under here. They didn't give me an equation, so I can't find an exact answer, but I can definitely estimate it because it looks like this is approximately a triangle, right? Area of a triangle is 1/2 base times height. In this particular case, it's going to be 1/2 times a base of 30-ish times a height of about 16. 1/2 times 30 times 16. That's the same as 8 times 30, which is 240. Right there. 240 ounces changed in weight. Net change example, word problems. Word problems sometimes scare kids. Read it, understand it, it's not so bad. This one is a little bit more complicated, but it still isn't bad. So let's read it, make sure you understand it first. Suppose an above ground pool is punctured at noon and water begins to flow out of the pool at a constant 0.8 gallons per minute. At 2 o'clock, the puncture begins to widen and water starts flowing through the hole at a rate of R of t equals 0.8 plus 0.0012 t squared gallons per minute, where t is the amount of time in minutes since 2 o'clock. If the pool started with 12,000 gallons of water, at what time will the pool be empty? So I've got to figure out when the amount of water in the pool is 0, when is it empty? So I know I started with 12,000. So if I were to write, I would probably start with an equation. I would start with 12,000, right? I'd say, hey, that's how much I started with. I think I've got that in here. That's the initial amount of water. And then I know I lost water. From noon until 2 o'clock, I lost some water at this rate, 0.8 gallons per minute. So I got 0.8. I'm just going to do the integral from 0 to 120 of 0.8 dt. 0 to 120 because that's 120 minutes, right? This was gallons per minute. And it's 2 hours, 120 minutes from noon to 2 o'clock. So this is the amount of water I lost during those first 2 hours. That's why I'm subtracting it. After the 2-hour mark, and once I hit 2 o'clock, the rate of change of that water loss shifted. It became this expression. So I got to find the integral of that expression. I'm starting it from 0 going to x, starting at 0 because this equation has time t being the minutes since 2 o'clock. Well, at 2 o'clock, that's starting at 0. But I don't know how long I'm going to lose water. I just know I'm losing this water at this rate for x minutes until the thing gets empty. That's why I put it to an x here. That's the water I lost during the x minutes after 2 o'clock. If it asked me how much water was left in the pool at 3 o'clock, this would have been easy. Instead of putting an x there, I'd put a 60 because that would have been 1 additional hour losing it at this rate. But I put an x here because it's asking me when it's empty. So I really want to know when this whole equation is equal to 0, right? I want to know when I don't have any water left. When I've had that 12,000, I lost this amount, and then that amount reduced everything left down to 0. So I took this equation, I put it into my calculator on Desmos, which I will share with you now. Right there. And I adjusted the scale, so we can see here started with 12,000 gallons, right? So that's right at time equals 0. There's my equation, same thing we had before. And I can see I lost water, until right down there. See if I can highlight that. Yep, right down there is where I hit a 0 right at 307 minutes. So it was 307 minutes after 2 o'clock. 300 minutes is 5 hours, right? 300 divided by 60 is 5. So that's 5 hours after 2 o'clock. So just at 7 o'clock, just after 7 o'clock, I had lost all of my water. That's when the water got down to 0. All right, moving on. Integrals as accumulation functions. This is kind of a classic accumulation. It says, let the graph of the function h consist of a quarter circle and 3 line segments as shown above. So something like that, quarter circle, line segments. Let g be the function defined by g of x equals -1 to x of h of t dt. So this is just accumulating area, accumulating net change, starting at -1 right here, moving on to the right of this function, right? So just kind of adding that starts. So if I went from -1 to 1, right, that's going to be a negative value because it's below the x-axis. Then I'm going to start adding quote unquote positive area. I know we don't think of that as positive, but that's above the x-axis. So then it'll start getting positive until it balances it out, if ever. This particular question, though, is asking for g of -5. What people tend to do is they start at -5 and go to -1. Be careful, g of x is the integral from -1 to x of h of t dt. So if I wrote that, that's -1 to -5, starting here and working backward, which we can do, but why do it that way? We've got properties of integrals where we can switch those units. Instead of going from -1 to 5, I know that's the exact same thing as going from -5 to -1, but having that negative on the outside, right? That's one of my properties of integrals. So I just need to find the area that's happening here. Well, that's equal to pi, this part here, because it's a quarter circle, right? And I've got it hidden here somewhere. There it is. Oh, that's for a half circle. That should have said 1/4 pi r pi 2 squared. The pi is right. I just forgot to put a 4 here. My bad. I want to cover that up. I'm not gonna waste time. Got short enough time, right? Let's move on. This is 1 because that's a triangular shape. Area of a triangle is 1/2 base times height. In this case, 1/2 times a base of 1 and a height of 2. That's a same triangle, except it's got an integral value of -1. It's -1 because that's got a base of 1, but a height of -2, right? That's going down, so that's a distance of -2. 1/2 times 1 times -2, that's -1. If I wanted to find this integral, that would be pi plus 1 plus -1, so just pi. So my final answer is going to be -pi because that made it negative. That is the value of g of -pi. One thing with these accumulation functions that get people is problems like this. It says find all values of x over the integral where g is decreasing. And students start to be like, all right, well, this is accumulates area, so I'm going to be accumulating negative values here, so it's here, and then they try to work that out. Instead of doing that, just realize what it's asking you. If it ever asks you for increasing or decreasing, that's the derivative, right? So it's really asking about g prime of x. I want to know when g prime is negative. Well, g of x is this function, so g prime is just the derivative of that function. We know this. That's our first fundamental theorem of algebra, our first fundamental theorem of calculus. If I have the derivative of an integral from some constant to x of h of t dt, that's just h of x. So when it asks find all values of x over which g is decreasing, it's really asking, hey, when is h negative? Because g is decreasing when g prime is negative, g prime is h, so this is just asking when h is negative. I can look at this like, oh, well, h is positive here, it's positive there, it's only negative during this section here. So I'll be like, oh, well, then it's g is decreasing over the interval -2 to 1, right? Because that's the interval over which h has negative values, and h is the exact same thing as g prime. Okay, I think we're going to make a good time this time. No half hours for you. That's good. Average value. Warning, don't mix these up. There is a difference between average value and average rate of change. Definitely make sure you are understanding the question and which one it's asking for. Average rate of change is just slope. F of b minus f of a all over b minus a. You should know that formula. Average value, that's the integral from a to b of f of x dx all over b minus a. We talked about that last trimester. If you want a quick recap for why that's average value, you can Google it or meet me during my office hour at 1 o'clock. I'll be happy to explain why it is. But I'm not going to recap why again right now because I want to try to keep these reviews short. I don't want to waste people's time. It is, so average value example. The altitude of a hot air balloon is modeled by this equation. That looks ugly, not fun. Where h is the altitude of the balloon in feet, t minutes after takeoff. What is the average altitude of the balloon during the first 2 hours of flight? Again, this year's AP exam is calculator allowed entirely, so why not make use of a calculator? Here we go. I've put that same equation for height right here. It was asking for average value, so I know average value, that's the integral over the period divided by b minus a, right? So I just need to calculate that fraction. I'm going to come over here, functions. I want to find the integral from 0 to 120. I believe it was a 2-hour flight and time was measured in minutes of my function, which I could do a cut and paste, but this is kind of handy since this was called h of t here. I can just write h of t dt. And I want to take that integral and I want to divide it by 120 minus 0, right, the endpoints. Turns out I have an average height of about 168.438 feet. I can take a look at that just to make sure. It's always nice to check. Here I started at a height of 0, went up and up and up, peaked out at a height of about 300, started going down again. Yeah, average height of 168 right here. So that seems reasonable. Yep, 168.438 feet was my average height. Last type of problem is rate of change problems. These don't have to do with integrals, but they are often in the same types of equations to make sure you understand the difference between average value and average rate of change. Same balloon, still going up, but this time it's asking what the average rate of change is of the balloon, and it's asking is the balloon ascending or descending in the altitude at the 2-hour mark. So two different questions with the same problem. Average rate of change over the 2 hours, and at the very end of the 2 hours, is it going up or going down, and at what rate? Here's the same problem. Get rid of that average value. You don't need that anymore. This time I want to know average rate of change. It looks like on average I was going up, right? And I definitely ended up higher than I started. So I use my average rate of change function, h of 120 minus h of 0. And I'm going to take all of that and I'm going to divide it by 120 minus 0. Looks like an average rate of change of about 2.37 feet per minute. Seems reasonable, right? Going up and up and up. Not super fast, but reasonable. The second part of the question asked at the end, right at the 2-hour mark, was I going up or down? I can look at this and like, oh yeah, I'm definitely descending, right? I can look at it and say, but then at what rate? Well, if I want to know at what rate at a very particular point, this isn't going to cut it. That's average rate of change. I want instantaneous rate of change. Instantaneous rate of change is the derivatives. Particularly, I want to know the derivative at the 120-minute mark. Right there, negative 1.99 feet per minute. I like seeing that this is negative because that means it's going downward, right? And my rate of change is negative, so I'm like, oh yeah, that must be the right number. So then going back to my problem, we'll finish answering it and we will be done here. All right, so what is average rate of change in the altitude? That was one we found when we did these, 2.37 feet per minute. Was it ascending or descending at what rate? H prime was negative 1.991 feet per minute. When I write this answer, I'm going to try to use the language they were using. So I'm going to say it was descending at a rate of 1.991 feet per minute. I'm not writing negative because I'm indicating that by using the word descending, right? I'm descending at that speed. So a speed is always positive, right? Speed is absolute value of your derivative. So descending at a rate of 1.991 feet per minute. That's it. You have an assignment that's a worksheet this time. It's called the Applications of Integrals worksheet. Download that, turn it in. As always, if you have questions, meet me anytime during my live hour. I'm here the whole hour. Meet me during my office hour from 1 to 2. Links are in Schoology. Good luck.